So my name is Chihani, and I'm going to talk to you about formal methods in their application for trustworthy AI. And as I said, this talk will be with minimal technicalities, so I hope you don't need a background to understand it. I'm gonna do a little deviation through a moment in history of formal methods that I think is relevant to what we're going through now. And then I'm going to give a global overview of the discipline, give a real-world example to be a little bit more practical, and finish with some of the challenges that we see in the near future. So let's start with what are formal methods. Generally speaking, formal methods are based on math and logic, and they are applied to the validation, specification, different steps of the life cycle of software and hardware. And we use them because they can offer formal guarantees on the requirements of these systems. And this usefulness is reflected in the fact that more and more standards are encouraging the use of formal methods in this development process. So I'm going to focus on two formal methods in this talk. The first one is formal verification. Globally speaking, formal verification, you have a program that is designed to be run on a set of inputs. You have a specification for that program. From that, you encode them in certain languages that are, let's say, adequate for certain tools of formal verification. And the goal of this is if you have a positive answer at the end, you know, or you're as sure as you can be that the program satisfies the specification. And if not, then you can either, sometimes you have a timeout, and some tools can give you a counterexample, meaning they give you an input that violates the specification. The other method that I'm going to talk about a bit is property-based testing. So in this method, you take the specification, and based on that specification, you generate inputs automatically that try to cover as much as possible that specification to test your program. So here, for example, we have a partner that said my system has to be. It is part of the specification of my system that it has to be robust to different lighting conditions, so darker and lighter images, because it's used throughout the day. And so what we did is generate images with varying degrees of lighting conditions, and that allowed us to compare several models that were designed for that problem, and see that the orange one is much frail to this type of differences. So now, to the moment of history I was talking about, and in particular to the end of the 70s. Nice. There's a problem in the slide. So if you can't read the line there, the name of the paper is a Social Process and Proofs of Theorem and Programs, which had this very provocative quote: "Program verification is bound to fail." Needless to say, if that were true, then this talk would be half as long. And you might think this is an obscure prophecy from an unknown paper, but actually the people who made this prophecy are big names that you unfortunately can't read. They're Richard DeMillo, Richard Lipton, and Alan Perlis. And they all worked at prestigious universities, and one of them was the Knuth Prize winner, one of them was the first recipient of the Turing Award. So you can imagine the influence that this paper had on the language that we use in formal methods. And let's say when a term becomes toxic, when you associate stigma with a term, then it can influence the university courses, it can influence the PhD subjects that the students choose. So it can of course reduce the funding opportunities, because you fear of losing credibility if you use this type of terms. I didn't put a timer, I should have. And so you can read more about it in this very good book that called Mechanizing Proof by Dalton McKenzie. It's not a non-technical book. It's more of a sociological and historical look at the evolution of formal methods. So yeah, those who work in AI can relate to this type of problem because this is what happened for the AI winters. We didn't reach that, probably because formal methods was never as fashionable as AI, but we definitely felt the slow movement at some point. Fast forward around 20 years, and we have this seminal accident. It's very important for the formal methods community because it's one, it could have been avoided if we had used formal methods. And two, it is the first example of the large-scale usage of formal methods in a real-life system, and in particular abstract interpretation, which I'll talk briefly about afterwards. And it's also a good example to scare students. So I know there are students of Super-Héros here, so... So the reason I'm talking about this is to say we have come a long way. So the evolution was very long, and the formal methods community, when I say we, of course, I was young at the time, but formal methods community worked hard to achieve these results. Now it is used in many industrial sectors. Some of them are here, some of them work with CEA in this subject, because CEA, along with the academic community, of course, developed tools, industry-relevant tools to tackle these problems. And the reason I talk about this is because with AI, all the tools that we made were specific to human-written code. By the way, I should probably change this slide because this is not human-written code. I mean, it is human-written code, but if you write your code like this, you get fired. It's not a way to write. But the goal of this slide is to say we have evolved a lot, but we have evolved by looking at the type of problems we needed to tackle, and we adjusted our tools with regards to that, and now we have a new challenge, and our tools don't work. Most of them don't work. So we need to do the work that we did before. And we know that there are miles and miles between theory and practice, but we also know that we walked these miles, so we kind of know the way. This is why Bertrand said, I'm optimistic because we went through this already. The first solvers, SAT solvers, for example, for those who know what it are, but they are solvers, weren't as efficient as they are today. They weren't efficient at all, actually. But today they can handle millions of constraints, and that happened because we looked at the problems and we found heuristics, we found clever algorithms to deal with these problems, and we can do the same for AI. And it's actually started. Just in the past few years, we have more than 20 tools that seen the light of day, that were published, and each paper that's published increases the scalability and efficiency. The good ideas that are developed in one tool are redeveloped in others so that all the community can advance. We have the niche creation in the sense of some solvers get specialized in some type of activation functions, some type of models, etc. And there is an adaptive pressure on the formal methods community because, as was said before, the field of AI is very fastly changing. So we need to be able to always keep up. And this effervescence is reflected in the number of the avenues of publication that were organized recently. Some of them are specific to formal methods, like the fourth and the fifth here. Some of them were co-organized by CEA. The first one was also organized with INRIA. And in addition to these, we have of course, we are welcome to publish formal methods papers applied to AI in formal methods conferences, workshops, symposium, etc. So now, after this, a global view of the discipline. So I always feel validation is a three-players game in the sense of you have, on the one side, the object to certify, which is developed by the developer or the client or the industrial partner. You have the methods and the tools. These are developed by us. And then in the middle, is where most or a good portion of the interaction happens. It's where we have to meet together and we have to lay down what is it exactly that we're trying to prove, or what is the validation process that the partner needs to follow, and how can we formally specify these properties in order to be able to deal with them. So I'm going to talk about the property, the specification problem that we have in AI right now. And the properties can be widely separated in two. The first ones are what is formally specifiable, and these are the type of problems where the inputs have immediate semantics. For example, we have here an ACAS, which is an air collision avoidance system, that basically takes as input a distance, an angle of approach, a speed, etc. And outputs directive to change course if a collision is about to happen. So here in this problem, the terms of the specification, near and approach in from the left, etc., are related to physical properties that are taken as input from the neural network. And so we can formally specify basically the whole system, and therefore we can verify it. So this is the ideal scenario. And you have sensory inputs, which are a bit harder to tackle. And this is because the semantics of what is inside an image, for example, is not seen at the level of the pixels. So the encoding doesn't have that semantics. So what you can do is specify properties based on these pixels. So for example, you can talk about the distance from an image to another image in terms of the number of pixels that you have to change and how much you have to change them. But what is inside the image is not, you can't say, for example, if I have a pedestrian, because a pedestrian is not a formally specified term. And so for these things, what we can do, so if we look at the machine learning as an example, the problem is this. I'm trying to be as general as possible, but you have a distribution on which you want your system to be able to generalize or to deal with. And so what you're going to do is select a certain number of inputs from that distribution, and you're going to train your network on it. And ideally, what you would want is for it to cover as much as possible of that distribution. So, of course, ideally, it could cover the whole distribution, but that rarely happens. So what you want is something like this, but what we don't want is something like this, meaning the system only knows what it was trained on and nothing more. So what you can do here is first ask yourself how it behaves in the neighborhood of certain selected inputs. And so you pick a distance, epsilon. As I said before, distance can be the number of pixels that are changed and how much they're changed, etc. And once you have that distance, it is a formal specification, and so you can prove it. You can either verify it completely, you can verify the neighborhood, you can verify that the system on that neighborhood is well behaved, which gives you formal guarantees but can be costly. And then you can also test. So based on that distance, you can generate inputs. So you're not covering all the neighborhood, but you can try to take as wide as a distribution as possible. This doesn't give you a formal guarantee on the neighborhood, but it can scale much faster, and therefore you can also pick wider distances. So why do we do this? Well, it can help you detect this type of problems that I talked about before. But if you pass the test, if all the selected data are, or if your network is robust in the neighborhood of all the data that you selected, it doesn't necessarily mean that it's general completely, right? If the distribution, again, I'm talking about sensory input, of course, if it's a formally specifiable property, then you can do it. So it doesn't imply this. You can also generate data from acceptable transformations. So these are the tests, the property-based testing I was talking about. For example, if you have images and you want your system to be robust with regards to blurry images, darkened images, etc., you can use this property to generate images. Hopefully, what you're trying to do is cover as much space as possible from the distribution. Again, so it's the same with the same goal. You can also mix and match. You can use the property-based testing to generate new inputs, and then you can verify the neighborhood of these inputs. You can also encode the transformation in a property that you can give to a formal prover. So you can, there are different ways that these things can be combined. And you can also use a simulator. So some people use a simulator or generator as a specification. So we had an expression of interest actually that was around that. And so what they did basically is use a generative adversarial network to generate a whole bunch of images. And then what they do is they consider the network as a specification. So what they say is all the images that can be generated by this network, my network knows how to deal with them. So the verification problem that I showed before, where you had the program and the specification itself becomes the model as well, and you have two models to verify in conjunction. So this can work. Right now, they only use MNIST, I think, if I remember correctly. I'm sorry, I forgot the name of the team that does this, so if you are here, just raise your hands. Right now, it's for small use cases only, but as I said before, scalability is not a really big roadblock that scares the formal methods community, because we've dealt with these problems before. But the question is, in the case of you take images and you verify the neighborhood around images, you can actually look at the images and you can spend some time selecting the right images that are wide enough to cover your distribution, etc. But for a generative adversarial network, I don't know if you can, I mean, the question still remains whether or not that can serve as a specification. Right. So this is as a side note. All the things that I'm talking about focused on the validation. So once the model is present, how can you validate it? But all this can also be, well, yeah, all of this can also, or the transformations of this can also be used in the previous steps of the conception. So, for example, in the selection of data, you can use the property-based testing to generate data to train your network. So this would be EC5, if you remember the sub-programs that we talked about before. You can also use some of these things to train your network, and you can even use the intervals that I talked about before to actually train your network not on individual inputs, but on neighborhood, on whole neighborhood around the inputs. That has problems of scalability, but it gives you a robust by design network at the end. So now the methods, I'm just going to talk about one, which is abstract interpretation, and I'm going to say high level. And abstract interpretation is used to be able to verify properties on whole inputs, on whole intervals of inputs. So for example, if you have an X that is between A and B, and a Y between C and D, you want to verify the program on all the inputs that are between these bounds. So what you do is you propagate these intervals through all the operations of the program. Here you have the example of addition, which is the simplest one. Multiplication is a bit harder. Then you go into loops and conditions, and it gets really messy. You can also use more sophisticated domains than just intervals, of course. And the one thing you can do is also to intersect these domains, the different domains, regularly to keep them as refined as possible, because the goal is to say as precise as possible. Because this is an over-approximation. So what you can have is, if you're not precise enough, I'll say that in a minute. The goal of this is, suppose the concrete or the real behavior of your program is the yellow part. What you do with abstract interpretation is you over-approximate it conservatively, so that if the over-approximation is in a safe space, you know that the real program is also in a safe space. The flip side of this is if you're not precise enough, so this is why I talked about before about the several domains that intersect with each other to stay as precise as possible, because if you're not precise enough, then you can have false alarms, meaning the system cannot conclude that the abstraction is safe, but the concrete program itself can be actually safe. So the goal is to try to over-approximate, but stay as precise as possible. But of course, the more you try to stay precise, the more costly it gets. And so you have to play with this trade-off a bit. And you can use the same for neural networks. So, for example, if you take as an input this 8, and you can encode all the possible modification that this input can have around a certain, with a certain distance. And then you can propagate all these intervals through the network, because the network is just addition multiplications and non-linearity, which is a real problem. And then at the end, if the over-approximation is still in the right classification that you want, then you know that the real execution of the neural network will always give the right result. If not, you're not sure that you don't have a guarantee. It doesn't necessarily mean that it won't work, but you don't have a guarantee. And in some cases, you can actually generate a counter example, but that can be sometimes costly. Now, I could give you a lot of references for formal methods applied to a neural network. I put here also symbolic execution that can be used. There are also SMT solvers that can be used, mixed integer programming. A lot of things can be used, but you can just go read the reports that we did this work already in Le Grand Défi. We analyzed the state of the art, so you can read the report that should be public, right? Yeah. No, not public. Okay, then I'll keep this longer, but there are a lot of other references I should have asked before. And as a side note, this is not a complete picture, because when you deal with software, you don't just deal with the source code. You have to deal with all the compilation steps all the way to the machine. And so, for example, there are people who showed that even if you verify your neural network, if you don't verify it at the level of the floating point encoding, it can still have problems. And at CEA, we try to cover these things. We have tools that deal with even the binary level. We have BANSEC. We have also people looking at the verification of parallelized programming, etc. So you have to keep this in mind. This is outside of my talk, but you have to also keep this in mind. Now, for the real-world example, how many time do I have? 5-10 minutes, okay. So the real-world example, mooring line failures. Basically, in the oil drilling, instead of using very big platforms that you put in place that are fixed, that don't move, what you can do is have a floating platform. So the floating platform moves from well to well. When a well is expleted, it goes to another well. And they're basically just very, very big ships, and you absolutely need them to stay in place. So, because of course, if they move when there's a storm, then pipes can break and oil spills can happen, etc. So what they do is fix them, moor them basically with anchor chains, and the chains are enormous. I mean, a single link of the chain is as big as a human being, and they can be more than 1 kilometer long. And so what you need is to check if these lines can break. So monitor these lines, because sometimes the break can happen at the end of the line, so you don't really see it when you look at the chain. So what you could do is fix detectors on the chain, but any detector that you use that is close to salt water doesn't last more than a year, so you have to find another way. And so what they did is rely on the motions of the platform, long-term motions relying on dual GPS. And they give that to a neural network, and the neural network, or they train the neural network with different weather conditions, different sea conditions, etc., different mooring line tensions, etc. And that neural network can help them detect mooring line failures in different groups. And once they had that, they came to us to verify the robustness of. There are many properties that I cannot talk about and results I cannot talk about, but one of the things that I can talk about is the robustness with sensory sensitivity. So the GPS location was correct with a certain error, and so what we did is include that error in the analysis, and at the end we were able to show that the system was more or less robust in that error parameters. So still a long way ahead. Challenges. One of the big challenges that we have is that in software, human written software, traditional software, what you can do is divide it into smaller and smaller bits. This is also something that was mentioned this morning. Smaller and smaller bits, each bit with bits meaning function, model, modules, etc. Each with specification, and you can prove them separately. And once you prove them separately, you can prove the glue that holds them together, and you have a proof of your software. And if at some point you need to change a function, because you found a better algorithm that is more efficient or something, you only need to redo that particular proof, and then you have the whole system again. With AI, things are different, of course. So with symbolic AI, it can still be done. We have a framework called Colibrix, where basically you have separate bricks for each of the domains that you might use. And the goal is for us to be able to, basically, if a partner comes and say, I have an application that only needs floating points and arrays, then we pick the floating points, domains, propagation, labeling, etc. And we do the same for array. We put them together, and you have a tailor-made solver. So you can still do the same thing because they're separate bricks. With machine learning, I don't know how to do that yet. We're looking at some things, but for example, if you trained your neural network on faces and then you wanted to retrain it so that it can also recognize faces with mask, how can you do it without losing the properties that you've already proven? Right now, the best thing you can do is just reprove the system. It would be good if you could, detect the properties that you no longer satisfy. Another challenge is a bit social, which is with traditional software. A company invests a lot of time and money into writing, a system. And so when a new, let's say, programming language arises, like Rust, I don't know, EDF or Thales, or they're not going to say, we're going to recode all our system in Rust. They're going to think twice about recoding all the system in Rust because they invested so much time. With machine learning, if there is a new, very efficient model that is very different from the current models, all you need is, of course, machine learning experience, but the heavy lifting is made by the machine that trains. Once you selected your data, you already have your data, you can redo the whole thing. And so if you design tools that only deal with the current models, without trying to look ahead at the models that can be used in industry, like recurrent networks and graph networks, you might be left behind. And of course, you have the other challenges, the scalability. We're trying to look at clever heuristics, parallelization. We also try to focus on community building, because that's also what lifts all the community. And we also try to invest time in the formation through university courses, tutorials with INRI as well, tutorials and conferences, etc. And so to conclude, I can summarize the whole thing, the whole fourth or five first points by a lot of challenges towards the formal methods application, but we're working on it, and we have very good signs. This is why we're optimistic. And Confiance.ai is, I think, really an excellent environment for this, because we have access to all these industrial partners with industrial real-life use cases that we can work on, and we also have academic partners to work with us on the scientific side. Thanks.
Thank you. Thank you very much. We take 5 minutes for questions. So I already see one here. The time needed for the microphone to reach you, I will ask you one question, but then you will be second. So this afternoon we have three workshops, but two are maybe related to what you say. One is on robustness, so of course it's here. But the second is on explainability. So any link between formal methods and explainability?
There can be, yes. So we have a thesis with Limag at CEA, a very brilliant guy. What we're trying to do is use the explainability in formal methods. So basically rely on, but again, we're going to need to take as granted the explainability part, right? Once we have that, we can use that in formal methods. That's one thing that we're looking at right now, yeah.
Okay. So thank you for the talk. So Adrien Gaufriot from Airbus. Yeah. So you know that in Airbus we are in love with formal method. We use it a lot, and I am part of this team that is using the formal method. Just one question. I come back on your slide when you compare, I would say, legacy formal method with the new one. And in fact, you say that on your slide, you present that in legacy formal method, in fact, you are analyzing the C code or the binary code. And actually, for formal method on artificial intelligence, you are analyzing the model that is not the final code. So my question is why we are doing that, and are we able to analyze finally the C code or the binary? Because at the end, what is inside the target, this is not the model, this is the C code. So what does it mean to analyze only the model, and what are the consequences on the proof that you are able to prove? And the second part is, at the end, do you think that we will be able to analyze the binary or the C code for artificial intelligence? Thank you.
I'm an optimistic guy, so I'm going to say yes to the second question. To the first question, the reason we start with the model is because it's the entry point. This is why we also have a pharmacy for the C code, is because you also need to verify the source code. The thing is, you have a very high-level specification that you divide into smaller and smaller specification, that you connect with different bits of the code, and then these specification, you need to also translate it into smaller and smaller specification to go to the binary code. I don't see how you can forget about the first part, the model part and the source code part, and just go to the binary, because it is efficient, or it is useful to go from the high level to the low level, going through separate steps. This is also why we have separate steps of compilation, because each step can do things, right? You have, yeah. Yes, of course, yes.
So
exactly.
There are people looking online, so if you please repeat what the question is.
So basically, you just said that you also need to deal with the low level. I'm agreeing with that, but and we have people working on that as well, and a lot of people are working on that as well. And it is absolutely an important thing, but you also need to verify the model. So right now, the problem of verifying the model is not completely solved. And as I said, we're working on the verification of parallel programming. The binary step of AI is not yet on, we are thinking of it, of course, but we don't have time to dedicate to it now. The thing is, if you can't verify the model, the other steps are, kind of lost, right? You have to be able to check each step that you make. But I agree with you that without that last step, a lot of what we're doing is dodgy. Yeah.
Yes, so I think we are not going to get rid of DOS 178 anyhow. But my question is to complete your challenges. You mentioned that one option was to build a specification using a neural network that would be the specification in the end. But being in the industry, you know that specifications are texts and documentations on which people have to agree and discuss those specifications. So my question would be, your model is going to be a model of what? A specification of what?
This is why I said can we keep the slides? I'm not Steve Jobs. Thanks. This is why I said people are looking at this, and the thing is, it is at the beginning of a discipline. It is nice to keep all options open, but this is one of the options that doesn't satisfy me either, because the specification that you start from are text, and you have to agree on them, etc. The people that look at this try to find, so basically what can happen, what is possible to happen, is that the problem of AI forces us to find new ways of specifying. If that happens, then this might be useful. If that doesn't, if we can find a way to deal with specification without relying on this, of course we won't rely on this. The thing is, if you don't have a way to specify your perceptive system, I don't know how to go from there. So right now we're keeping all options open. I'm not working on the GAN thing, but I think I'm always so. Fundamental research can sometimes branch into different things that die off, but it's very important to look at these things as well.
Yeah, thank you for the very interesting talk and very great to understand. On this slide, I think you showed that you are using the distribution to assess, formally assess the model. Yes, and my question is, how do you construct this distribution space? For example, if you take an image, do you take image metadata? Do you take embeddings from a neural network? Or how do you construct this distribution?
So to construct a distribution, you basically take whatever the network will be run on. So if the network will also have metadata as an input, then you also use that, yes. If it's just the images, anonymized data and stuff, then you just use images. It depends, basically it depends on what the model is going to be used on afterwards.
Well, thank you for the presentation. A property that I find to be interesting in robust, in people working on robust optimization is the ability to, in addition to specifying or to verify some property, in addition to optimize the parameters to be able to fulfill these properties. Is there any way to do the same with formal verification? Like you cannot, for instance, you cannot reach the verification step at the moment, but if you change these parameters this way, then it's going to work.
So thanks. What was it? Was this? This is. I think that you're talking about this when I talked about the intervals. So the abstract interpretation that I talked about, the fact that you can propagate intervals, you can do it during training. Sorry, you can train your network on intervals. That way, if you want it to be robust with a certain perturbation parameter, you can use training to do that. But of course, the other parameters are still important: the efficiency, the precision, etc.
I was talking about the parameters of the model. Can you optimize the model in such a way that it verifies some properties?
Sure. Yes. You can also have a so I didn't mention this, but there are people working on I think it's called differentiable logic, where you train your model on a specification. You give it a logical formula, and you tell it to train with this logical formula in mind, so that at the end it verifies it. So yeah, you can do that too.
So this will be the last question, and then we move to the next sequence.
Mm-hmm. Yeah, thank you. I'm Armin Dietz from Capgemini Engineering. I have a question regarding your methods, like to extend the distribution, and you're using like data augmentation methods. And as I understand, if I understand correctly, it's like a posterior method to verify that you're in the domain. But wouldn't you, as a data engineer, like when you create your model, try to have all this distribution already doing training? So any data you are able to generate, you would try to train your model on, and it would already be inside that distribution. So the actual problem is more data that you are not able to generate, no? That's like this conflict.
So first of all, I'm not a data engineer, but this is the thing I'm talking about. For validation, I think one thing that is important is to try to see if your network can generalize to things that it didn't see. If you include all your data you generate, and you include all your properties of robustness in the training, then how would you, that becomes of the universe of things that it knows, and how can you test then that it can generalize? This is the reason why we have validation sets in training, right? You need something that it didn't see. If you put everything you generate in the training, then you might have a. But it's something that actually is interesting to me. I want to. I don't have the time, but the one thing that I really want to know is exactly how much it affects the system if you do that, with the trade-offs you can find between using it at the training and at the validation, the type of transformation you can use, can you use just different distance of perturbation for each of the steps, how can that affect the robustness of the system as a whole? That's actually very, I think, very interesting, but fortunately I don't have the time to look at that right now.
Okay, so for the remaining questions, you will talk directly to Zach. You're staying here. Huh?
Yeah.
Thank you very much. Thank you again.